So I'm Dragoslav from Kryptowire, and I've been working with Zane here from Georgia Tech and a bunch of other people on DARPA-funded Ops 5G projects. And for this, we actually needed to do some experimentation on security in 5G networks. So we're going to tell you a little bit about that. So we all know 5G is here. It's important. Most of the wireless research right now is actually being oriented towards 5G in some capacity. Actually, very recently, they changed this number from 5 to 6, but the research is actually pretty much the same. Security is still in its infancy, and in 5G we're still working on it. There's a lot of, it's a very active research field. And the problem there is there's really no good, proper way to test these security principles that people are working on and researching. Some solutions are closed source, so they're basically black boxes. You can't really do research on them. Some are extremely expensive, and many of the ones who are neither of those don't really work out of the box. Like you can follow all the tutorials, but it doesn't actually end up working until you do some fine tuning. So we decided to build our own test bed, and we had to accommodate some of the requirements of the project. So it has to be a realistic test bed. So fidelity is important to us. We used physical devices. We need to connect physical devices to our G-Node Bs. We also, for the purposes of the project, have to run some extremely large-scale experiments. So we also need to support emulation, and we use the physical components to verify the fidelity of the virtual components so that we can run emulation. And finally, maturity, meaning we want to support new, latest 5G standards as they're being developed. And finally, just to show you what the testbed actually looks like. So 5G introduced this thing called network function virtualization, meaning most of the proprietary network functions in previous cores are now switched to basically softwareized components called virtual network functions, or VNFs. And we run these VNFs as Docker containers. Those are these nice green boxes. And as we deploy our networks, we basically just run a bunch of different Dockers, and then there's more Dockers, and we finally get to the RAN where we can connect to the actual G-Node B. So now you can see that some of these boxes are green and some are blue. These green ones are actually shared between multiple slices, while the blue ones are slice specific. So when we run a new network slice, which Eric just explained a few minutes ago, we replicate some of these VNFs, and then we can run more slices for different service types. And depending on the service requirements, these VNFs can be run closer to the edge or further from the edge, depending on what we actually need to accomplish. There's different kinds of slicing topologies that we can run. And finally, we can also run, like if there is like a specific security requirement, we can run an isolated environment on different VMs or different hardware completely. And finally, we connect that to a G-Node B, which is in our case software-defined radio, and we can connect actual phones, or we can actually run this emulated with just more Dockers. And with that, I'll hand it over to Zane, who's going to tell you about some of the experiments we ran on this testbed.
I just use the mic. So yeah, you might be wondering, how can we actually use this testbed for security experimentation purposes? So here's one example of a defensive cyber operation called 5G network games. And this is something that we've actually implemented. At a high level, network games is the multi-step cyber operation of detecting, isolating, and then interrogating a network threat in order to gain new insights into attack vectors. So in this diagram here, we have a testbed deployment with multiple G-Node Bs connected to the 5G core, and each G-Node B has multiple UEs, which can be things like mobile devices, IoT, or traditional laptops and PCs. So each G-Node B here is programmatically configured to perform these network games. So notice that we have an infected mobile client on the top right. And the first step of these network games is to actually detect a threat using any sort of generic mechanism, such as a firewall that blocks traffic based off of a block list. And the second step here is isolation. So using this network programmability, the G-Node B can automatically drop all subsequent traffic to an infected device, which limits the spread of infection. The third step here is to dynamically spin up a virtual network fuzzer that can begin to play games with the infected device. So this can be something like a network host that returns different DNS responses to elicit alternate malware behavior. Or it could be a honeypot that entices the infected machine to interact more and reveal its tactics, techniques, and procedures. So now the threat intelligence generated by this network fuzzer can then come back full circle and feed back into the original detection mechanisms. And this can further propagate to improve detection for the rest of the network. Finally, one additional optimization that 5G affords us is the ability to perform stepping stone detection. So instead of running distributed threat detection at all Gnode Bs at all times, which is a challenge for performance and operational reasons, we can actually initially monitor traffic within the 5G core itself. And then when we detect a threat, we can activate additional detection and defenses closer to the threat source. So to make an analogy, detecting malware is often like finding a needle in a haystack. And rather than sifting through each of the individual pieces of hay at all times, we can use a metal detector that detects what region the needle is in, and then we can deploy or closely analyze only the region of the haystack that triggers the metal detector. And taking a step back, building out and testing this complex functionality in a realistic test environment is crucial because there's no way we could coordinate all the different components and work out the issues, the strengths and weaknesses of this system in a simulated environment and we wouldn't obviously do it in a production environment. So hopefully today's talk has convinced you of the importance of a realistic full-stack 5G testbed, and hopefully we've also given you a taste for some of the complex defensive security possibilities in 5G. Our code is available at this link, and we'd love contributions and feedback from you all, so please check it out. And ultimately, we believe this project can help enable the development of more resilient and secure 5G technologies. Thanks. Now, are there any questions?
Maybe some clarification between UPF and Gnode B. Were you doing this detection of evil.com on Gnode B or UPF?
I mean, we can do it in either place, but in this specific, in the first diagram, we're doing it at the Gnode B. This is kind of the more, we have a lot more distributed sensors everywhere. This is the inefficient version of things. And then the more efficient version is actually just performing detection initially at the UPF. And when we receive a hit or a signal, then we deploy more precise detection at the Gnode B.
Okay. So you're seeing this out of band, right? So it's not the CU or DU reporting back evil.com to you?
No, it's out of it, yeah.
Yeah. Any other questions? Cool. All right. Well, I think that's all we have today. So.